The next distribution that we're going to introduce here is the geometric distribution. All right, so this is actually pretty commonly seen in real life, okay? Let's just look at example here. A gambler plays at a roulette table and always bet on red until he wins, okay? So each round, so remember there are 18 red, okay, in the roulette table. So 18, and there are 38 in total. So in each round, his chance of winning is 18 over 38, which is 47%-ish, okay? So let X denote the number of rounds he plays. Okay, so let's keep in mind here we're using X to denote the number of rounds he plays. Okay, and remember the gambler going to keep playing until he wins. Okay, so with this in mind, let's look at the definition of a geometric distribution, because X in this case, in this particular example, can be described using a geometric distribution. So we denote the random variable that takes value. So again, it's integers, okay, but it has to start from 1, okay, because, well, the number of rounds someone plays in this game cannot be 0, just like Poisson, okay? But here, we're always taking integers, and it can also go up to infinity. So this random variable X is gonna have a geometric distribution with parameter, okay? So it only has one parameter, it's the success probability between 0 and 1, okay? If its PMF is this form. Okay, so unlike the Poisson, which might look a little bit complicated to even like think about why that is the case, I think here is much easier with the geometric distribution. So let's go back to the example above here. Okay, so every time, each round, he has a chance of winning of 0.7%, 0.7. Okay, so we use that as P. Okay, generically denote that as P. Okay, so the gambler gonna play it until he wins. Okay, so if he plays K rounds, okay, then if he plays K rounds and then he will win at the K round, what that means is that the first K minus 1 rounds will have to be failures, right? And then the last one has to be a winning, okay? So what that means is that the first K minus 1, okay, each of those rounds will have a failure probability, right? 1 minus P, okay? So for that to happen is 1 minus P to the power of K minus 1, okay? But the last one has to be winning, okay? That's what we mean by, well, he will play K rounds and then he will stop, okay? So because the K minus 1 rounds will have to be failure, so the chance of that is 1 minus P to the power of K minus 1, and then the last one will have to be a win, so we multiply with P, okay? So that's why the PMF, okay, of a geometric distribution is actually overall pretty intuitive to see, okay? And then notice that again, the range of the value that K can take. Okay, so keep in mind that this is what we call like a geometric distribution, okay? It is the random variable X itself, okay, is describing the number of rounds that someone plays, okay? So meaning that, well, the person will keep playing until he wins. Okay, so X is describing the number of rounds that somebody plays. Okay? So more generically, we can say that X represents the number of trials performed until we get a success. Okay, and again, P is the success probability on each trial. Okay, and even though we don't say it as much, as you can see that, well, P has to be constant, right? It has to be the same for each trial that we play, and each trial, just because as you see here, we're multiplying all of this, right? So we assume that each trial having a success outcome or failure outcome is independent from each other. Okay? And also just to bring your attention to the distinction between this geometric distribution and the binomial distribution. For one thing, you will see that the total number of trials is fixed, okay, for the binomial distribution. And if you remember, binomial distribution N is one of the 2 parameters that it has anyway. So for binomial distribution, it is fixed, okay? However, for geometric distribution, it is exactly the number of trials that we're actually trying to use the random distribution to describe for. So X, which is the number of trials, is random in the geometric distribution, okay? So this is first, at least one of the distinctions, okay? So I will also ask you to think about what would be other possible distinctions between the 2 distributions, okay? All right, and we're also gonna cover relatively quickly here, okay, that the properties of geometric distribution. So again, just like before, we put the PMF up here for you, okay? We're gonna refer back to this pretty regularly, okay? So there are two things required for you, okay? The first one is that it is well-defined, okay? Again, meaning that if I'm doing a sum of all of PMF, it should be 1. And again, here we're doing infinite sum, but k starting from 1, okay? And then you add up to infinity, okay? So to show this one, okay, actually it's relatively easier, I think, compared to the Poisson again, mostly because, well, as you will see that we're adding up the infinite sum, and then each of them is having 1 minus p to the power of k minus 1, then times p, okay? And you probably also recall in your sequence of series courses before that there is what we call like a geometric series, right? So to show that the geometric distribution is well defined, we actually will use that geometric series result. So let me show you here, okay? So again, we're trying to show the sum of this, okay? And in fact, what that means is that we have the p, okay, again, so you can think of this p, again, it's not about k, right? So it's a constant, so you can bring it outside of the summation, okay? And the summation, as we know, well, it's just 1, that's the when k equals to 1, right? 1 minus p when k equals to 2. So you are doing a geometric series over here, okay? And because of that, okay, you have p, which is this p, and then you're dividing by 1 minus p over here, okay? So that's a geometric series result, which is gonna give you a 1, okay? So that's the first required result that you need to know about the geometric distribution. The second one, okay, is to show that it's CDF, okay? Also, it's, well, if you look at this, you can probably use a series results as well, okay? But maybe even more quickly, another way to think about this is that, well, if I want to know probability of X, right? Smaller or equal to K, that's the definition of CDF, okay? It is equivalent, okay, to do 1 minus probability of X is greater or equal to K plus 1, okay? So this is using the complement rule, okay? So the probability of X is smaller or equal to K is the same as 1 minus the probability of that X is greater or equal to K plus 1, okay? And if you look at this, well, it is saying that the first K trials all have to fail, okay? And if that's what you're looking for, then it's just going to be 1 minus p, because that's the failure probability, to the power of k. Okay, so that's why instead of doing all of the series results step by step, you can maybe more quickly recognize that, well, using the complement rule, the CDF of the geometric distribution is 1 minus p to the power of k. Okay, so those are the two that is required, okay, for you to know. And the other properties of a geometric distribution is its mean and its variance. It's not required, but I show you the results over here. The mean is 1 over p, okay? And the variance is 1 minus p over p squared, okay? And you can consult the textbook, page 148, for the derivation for both, if you want to get those exercises.